for finite f, this would be, roughly speaking, would be root log cardinality of f divided by n. Okay, and so it goes to 0, and so the excess this goes to 0. The question is how can we generalize this to a more general function class where f is infinite dimensional. So we're going to focus on the case where the loss is binary. If the loss is basically 0, let's say 0, 1 loss, then this function class is a Boolean function class. So the domain is general, it's that z, but the codomain is 0 to 1. So then we introduce this idea of VC dimension for Boolean functions. I actually did this example, warm example. The proof is not quite correct. It's just, it's like hand-wavy proof. If you go through it, just want to point out that I did wave my hands to give you the idea, but we're going to do a proper proof. The issue was, this was the Gillenko-Cantelli idea, or the theorem that said that if this function class, let's say, is the indicator of half open intervals, half infinite intervals, then I can get a uniform control over this. This is a uniform sort of control. In that case, it would be the distance of the empirical CDF from the population CDF. And we saw that, roughly speaking, when I take f to vary in this class, these variables don't take infinitely many values. They take finitely, like at most n+1 values. But to properly write it down, it's not obvious. So this statement that I had is a little bit tricky. So just think about it. I'm going to talk about that in the case of VC dimension. But the idea of VC dimension allows us to do a proper proof. Let me go to the VC dimension and then we'll see. So the idea of the VC dimension was that if I look at the restriction of the function class over this, let's say endpoint set, so pick n points and look at the restriction of the function class over this set, that's basically what we encounter in these sort of random variables. So we're evaluating. So expectation is constant. You're evaluating the function over this random vector. X's there are basically z's, so there is a bit of discrepancy in notation. But the restriction of the function class to this endpoint set is another function class which can be viewed as subset of 0, 1 to the n. And in general, if the function class is rich, this restriction would be the entire 0, 1 to the n. And then there are some function classes for which this is smaller in general. So there was this definition that the subset of point is shattered by if I restrict it to any to that subset, then the cardinality is the maximum that can be to the number of elements in the set. So if an endpoint set is shattered by f, then this will be 2 to the n. If there is an endpoint set that can be shattered, then the VC dimension is at least that. So we go up until there is no endpoint set that can be shattered. And at that point, that's like like n-1 would be the VC dimension. So it's the largest n for which there exists an endpoint set that can be shattered. And so we saw that for the interval class, it was 1. For some of the classes we also discussed. And the proof, actually, there's this main result, which is Sauer-Shelach lemma, that says that if you have a class of Boolean functions on an endpoint set X, and the VC dimension is D, it's better to call it probably V for future reference, because D is usually the dimension of the underlying space. Then this cardinality is at most polynomial in n, rather than being 2 to the n. And just to remind you, the way that this was proved, the main ingredient is this result that says that if you have a function class over a finite set, the cardinality is bounded by the cardinality of this other set, which is the set of points that can be shattered by f. And if the VC dimensional f is at most, let's say v, then there are at most this many sets that can be shattered by this is like the number of all possible subsets of size of a set of size n, whose like size is less than v. So all the at most v sized subsets of the n-point set. So this is the immediate consequence of that. So this is saying that instead of so the worst case is much less than the worst case, 2 to the n. So it's instead, roughly speaking, it's like n to the v. Okay, polynomial in n, v usually is constant, like n to the 1, n to the 2, rather than exponential in n. So then we ended up arriving at this result, which, so roughly speaking, says that if the VC dimension of the loss class, this is the composition of the loss on the function class, this is what we called f. If let's say this is v, I should have done v, probably better to do v here, then we have a result like the high probability that the excess risk of the empirical risk minimizer will be bounded like that. So if you just ignore the constants, this is roughly, let's say, root log n, if you want n over divided by v, divided by n. Log n over n, sorry, there's a v as well. So it would be like root v log, ignore the constant. So this divided by n, it's likely, like if you ignore the log as well, it's root v over n, okay? And v is usually constant, so this is going to 0 quite fast. So to get an intuition for this, recall that for finite classes, for finite h, like we have finite loss class, finite f, which is LOH, and we get EH of h hat n is roughly root log h or f, so log f divided by n. And so for the class, so if f has VC dimension v, then let's say f applied to a set of point, in our case like z1 to n, the cardinality is at most by this lemma is at most e n v to the v. Okay, and if you plug this for the f here, and then you apply the log, you get this result. Okay. So roughly speaking, the VC class behaves like a finite class with this many points. But in order this, the reason why this is not just an immediate consequence of the finite result is that, and also the reason why the proof that I did was for the Gillen-Concantelli was hand waving, basically, is that this is only true if I fix the set of points. So I fix the set of points on that set of point. When I restrict f on that set of point, it's I can use these results, right? So I can say that. So this basically, there's like a little, like small argument here that when I restrict f to that class, the z1 up to zn, it's as if f is defined on an endpoint set, and then I apply this So VC dimension of restriction is actually, you can think of it as a new restriction, is like upper bounded by the VC dimension of F itself, and the VC dimension that goes here, and then it's going to find F is bounded by this. So that's that we can figure out. But the thing is that I have to fix this. If I change this, this is in general a random quantity. It's bounded by this, but it's random. So it's not exactly the case where you have just a fixed finite set of functions. So we have to somehow come up with an argument that I can sort of somehow condition on this, fix this, do the argument, and then get rid of the condition. But the thing is that if I condition on Z1 up to Zn, then there's nothing else left to do probability with respect to. Okay, so so we have to be sort of a little bit clever here, or people have been clever here. So that's the argument that I want to do properly, and then you get this proof. So this is not just an immediate consequence of the finite result, although it's just very suggestive. So if you just plug in the cardinality there, that would work. So any questions so far? Online people, offline people. Okay, so so that's where we need to like introduce some sort of empirical process theory ideas, which is useful in its own right. The nice way of proving it is via this idea of an empirical process bound. So that's what I'm going to do. So we're going to do like a shift of topic and then come back to the proof of this. So we need some more tools to prove this. So this is a reiteration of the slide that I had, the basic lemma on excess risk. Just to remind you, the setup, we're going to control this quantity down here, which is over the loss class. Sorry. Yeah, this quantity here. So now I'm going to introduce some notation. The notation might be a little bit abstract, but it helps us write things more clearly. So I'm going to introduce this notation in functional analysis, sometimes called the duality, which looks like an inner product. But the thing is that it's between something and its dual. So between a function and a probability distribution. So if I have a function and a probability distribution, I can define this sort of functional that takes the function and outputs a number. This is basically the expectation of f evaluated at Z1, where Z1 is distributed like P. P is like the underlying distribution. So if you think about it, another way of writing it is just it's just integral f z dp of z. So every probability distribution has sort of a natural functional associated with it. A functional is something that acts on functions. So you can think of a probability distribution as a functional. How does it like act on functions? By just integrating them against itself, and it just produces a number. So so this thing is a functional, like the natural functional. Associated with probability distribution P, and it's suggestive of an inner product, although it's not an inner product, but we can have something like a Cauchy-Schwarz, although it's not Cauchy-Schwarz, and things like that. So that's one notation. And then Z, capital Z is Z1 up to Zn is a training data. So Zi's are IID from P. And then I'm going to take another sequence of length n of IID Rademacher variables independent of Z. So Rademacher is just, so these are epsilon i's are Rademacher, IID Rademacher. And Rademacher is just uniform on -1 and 1. Okay, so epsilon I is Rademacher means that the probability that epsilon I is plus minus 1 is 1/2. It takes just like a random sign. Okay, I'll take another like IID sequence of epsilons, and I have Z1 up to Zn from my training data. And then I define this empirical distribution, which we've seen before. That's the empirical distribution or empirical measure, 1 over n summation 1 I from 1 to n delta Zi. And then I have this other notation that I introduced, which just adds these weights. So there's a sign I attach to each one of these delta sort of measures. So if you think of unidimensional, usually Z is not unidimensional, but so suppose you have a single, so Z is on the reals. So P would be like, P of Z would be something like that. So this is like Z1, Z, I don't know, 3, Z5, Z2, dot, dot, dot. So all of them have weight 1 over n, and delta is, this is just a measure that puts mass 1 over n at that point, Zi. So this is a probability measure. This other thing is not a probability measure, but it's a sign measure. And so some of them would be flipped. So this might be like this. The other one might be flipped. The other one might be flipped. So that's the empirical measure. Someone like assign a random sign to these. Okay. So these are not standard notation, but they're helpful. So associated to each random vector Z, we have an empirical measure, and associated to each pair Z and epsilon, we have the sign measure. Okay, has more sort of randomized version of PZ. Okay, so if you think of this notation, and if you take in general, when I apply F, like this duality to F and P, I'm integrating F against P. So if you think about applying this duality to F and this PZ, I'm integrating F with respect to PZ, which is just this quantity F here. Because it's a discrete measure, when I integrate a function against this, I'm just evaluating the function at point Zi with weights 1 over n. The same goes when I apply F to this measure. I'm just integrating out, but with these weights. Okay. So this is the notation. Is this clear? Right. So again, this notation is just, you can think of it as this being the distribution of random variables that takes values Zi's with probability 1 over n, and then I'm applying F to that random variable, take the expectation, which is going to be this. This is not a proper probability distribution, but still you can have the integral. It's just a measure. This is an integral. F against this would be that. And then one of the things that you can see is that this is a linear functional. So integrals are like linear functional. And it's linear, like it's bilinear actually. So this thing is bilinear form. So it's linear in both elements. So if I add like F, G, and then P, it would just like decompose F, P, and plus F, G, plus G, P. And then if you add like combine two P's additive, it just becomes like that. So I have this identity. So F applied to PZ minus P is F, like the duality between F and PZ minus P. I'm going to call it inner product for simplicity. Inner product of F and PZ minus F and P. That's by linearity. And then if you look at these expressions, so this is basically okay. This is by definition this guy, and this is by definition this guy, and then I can move this inside because this is constant. I can move it inside the sum. Right. So I have this deviation that I was looking at constructed. So this quantity, for every function, you get a number. So if you look at the map that maps F to this number, that's a process defined on the functional space. Okay, so you have the functional space F. So pick a function here, and then you map it to the reals by this F PZ minus P. So if you remember, a random process is just a collection of random variables indexed by some set. So if I call this, I don't know, WF, so we are looking at the random process indexed by F. So this is called the empirical process. So it's an abstract process. So the underlying randomness is the randomness from Z's, but it's just defined over the entire function space. This other sequence that we defined, you can apply this to F applied to this guy. So this would be so the process that maps F to this quantity, that would be a different number. So this is mapped to also like F and PZ epsilon. This is we call this, I don't know, VF. VF as F varies in F is called the Rademacher process. And these processes are very related to, I mean, very much related to each other. Okay. So the thing is, if you view it this way, what I care about, if you go back, what I want to control is the uniform, in the uniform bound is something like that. So this is basically supremum over F, if you want, of WF. I'm controlling the supremum of absolute value of this empirical process. That's where the empirical process theory comes in. So the quantity of interest for us is just the supremum of the empirical process over the function class. Okay? Notation is sort of clear. Okay. Another, like one more notation. I'm going to write for this supremum, I'm going to write it like this. So PZ minus P, the F norm. This looks like a definition of a norm. And it's actually a semi-norm. If F is small, if F is big, it's a norm on the space of like sign measures. But that's the definition. So basically, and this is the same definition. So you apply sup to this Rademacher process. I'm going to write it as the norm of the Rademacher process. So this is the norm of this deviation, and this is the norm. It's just a notation, useful. So the idea is to basically relate this supremum that we want here on the top to the supremum of the Rademacher process. And the technique is involved is called symmetrization. That's what we want to do. Yeah, one thing to note is that both of these processes are zero mean. So if I take the expectation, so you can see if I take the expectation of this quantity, the expectation goes inside the expectation of each one because of the IID assumption is the same as the expectation of FZ1. So this is zero mean. This is also zero mean, the Rademacher process. Why the Rademacher process is zero mean? Yeah, because these are independent when I move the expectation inside. So the expectation of F PZ epsilon would be 1 over n. By linearity, this goes in. I get the expectation of epsilon I times the expectation of F Zi, and this is 0. Right. So both are centered processes. But the symmetrization sort of symmetrizes the distribution in a sense. If I get a chance, I'll try to maybe plot something. Okay, so any questions? Have you guys seen symmetrization before? No. No. Online people, have you seen symmetrization? Let's see if anyone has seen symmetrization. No. Okay. Okay, so it's a very nice technique. Here the idea is this mean, so this P here, or if you want, when I look at this, basically, this quantity is a little bit bothersome here. Okay. The idea is to get rid of this. You can see in the Rademacher process, there is no expectation. So instead of being centered near the mean, we sort of center it in a different way, okay? Both are centered and then they're close, but this doesn't involve the mean of the random variable, which makes it much easier to control. And you can also see once I do this, I have an extra source of randomness. Then I can condition on Z and then use the VC argument. There's still some randomness remaining. That's the trick, basically. There's basically two. The main idea is to get rid of the expectation. And then so you can imagine what happens is that intuition, give you an intuition. So we have let's say I have an x minus the expectation of x. So what this is doing, like if I want to look at the deviation, so it could be I have a distribution like that. And this is the expectation of x, right? So this could be like 0 could be here. The expectation could be very large, but the deviation doesn't care where this expectation lies, right? So you care about how spread out you are around the expectation. Instead of looking at this, you might look at, let's say the absolute value of epsilon x. The epsilon goes away, but so what is the epsilon x? So epsilon is independent. So with probability 1/2, you would get something like half of this, and with probability 1/2, you would get the other direction, right? So when you add them up, so this is if you think of the distribution epsilon x, the distribution is basically, let's say if the PDF, if x has a PDF, the PDF would be 1/2 the PDF plus 1/2 the PDF reflected. It's just a mixture. So that would be something like yeah, it's hard to plot, but so it would be a symmetric distribution. It's this symmetrized version of it. So if this was originally symmetric, this would be like perfect. But in general, the thing is that this is going to be sort of bounding that distribution. That's in a sense what we want to do. So that's the meaning of the symmetrization. So you replace a random variable, centered random variable with a symmetrized version, which is like centered around 0. And then the main idea is that the expectation, the absolute value expectation, doesn't matter in controlling this deviation. So you don't have to worry about that. So symmetrized version. So let me try to do like the basic idea in a simple setup. Consider like x, let's say, is a real. So this is just is a real value. Random variable. And I form a copy of it, independent copy, which is x prime. So both x and x prime are from the same distribution, they're independent. And then I pick an epsilon, which is a Rademacher random variable, independent of, so this takes values plus minus 1, probably 1/2. Okay, so we have, yeah, so the question is, yeah, so this is the PDF of, well, actually, this is the PDF of x. The PDF of x, not the PDF of x itself. The PDF of x minus expectation of x would be centered around 0. The way I drew it, Said asked the question. This is the PDF of x, and this is the PDF of epsilon x. So the PDF of epsilon x is always centered around 0. The PDF of x is usually centered around epsilon, and sorry, around expectation of x, and but by this symmetrization, basically deviation, we like transfer it to the 0, and then in a symmetric fashion. Did that answer your question? Let me know. So, so x and x prime, if you look at the pair, it's an exchangeable pair. Exchangeable means if I switch, so what this means is that the distribution of x and x prime is the same as the distribution x prime and x. By independence and the fact that they have the same distribution, if I flip the coordinates, the distribution doesn't change. And because of that, x minus x prime and epsilon times x minus x prime, they have the same distribution. Anyone can sort of argue this, why this is the case? Yeah. Yeah, so for example, x minus x prime has the same distribution x prime minus x. That's from the exchangeability here. But I can also add epsilon here because once I condition on epsilon, I either see this or I either see this, and they have the same distribution. So conditioning on epsilon, conditioning on epsilon, because of independence, the conditional distributions don't change. We either see x minus x prime or x prime minus x, both of which have the same distribution. And the distribution of this guy is just the average of those two distributions, and those are the same. So you get the same distribution. So that's the key idea, that the distribution x minus x prime and epsilon x minus x prime is the same. And so consider any convex function phi. So the technique goes something like this. I want to compute the expectation of phi of x minus expectation of x. The first thing is that this expectation, so this outer expectation with respect to x, and this is also with respect to this guy, but this is like a dummy variable of this expectation. I can just replace it with x prime. Okay, so this expectation is with respect to x prime. Then the next step is that I'm going to pull this expectation out. So this is basically, if you think about this as x, let me do it maybe clearly here. So I'm going to do it with, sometimes I put x here to emphasize what this is with respect to. This quantity is the same as x prime. So if I take expectation of x prime with respect to x prime, that's a number, and then the expectation of the distribution x minus this, and then I have that. And then I pull this out. It's like expectation of x, expectation of x prime, phi of x minus x prime. That gives me an upper bound. So why this is true? I can pull the expectation out. Phi is convex. It's Jensen's inequality. So think of the this inner quantity. So you can think of, let's say, x as fixed, phi of x minus, let's say, u, defined as psi of u, fixed x. Okay, so we have psi of x prime, basically, less than psi of expectation x prime, less than expectation x prime, psi of x prime. That's what we're doing here. Okay, if you think about expectation of, and then, so this part basically, this and this, if you compare the two, expectation x prime, psi of x prime is basically the second quantity, and psi of expectation x prime is the first quantity. So like condition on x or fix x, because they're independent, you can do this. And then I'm applying expectation over x to both sides. So that's this quantity that I have here. So combining these two expectations, it's just the expectation with respect to all the randomness that there is, which is that. So that's the first step in symmetrization. So you can see I got rid of expectation inside. So now I'm looking at these deviations. I'm just now gonna replace this with the Rademacher version. So why can I do this? They have the same distribution because of this observation. And then I have this inequality there. So what is this inequality? Okay. Great. Yeah. So what we're going to do is that, so I'm going to write this as 1/2 this guy plus 1/2 negative. Actually, I have to do 2 here. 1/2 2 epsilon x plus 1/2 negative 2 epsilon x prime, right? And so phi of this would be, it's like phi of 1/2 x plus 1/2 y would be less than 1/2 phi of x plus 1/2 phi of y. That's by definition of convexity, right? So if I apply phi to this, I can move phi inside, and then I have an inequality, and then expectation goes applied to each one of the terms, right? And then I have this last line. So why is the last line true? Epsilon and negative epsilon have the same distribution. X and x prime have the same distribution. The independence of the distribution of what is inside is the same as this. So these two, basically 2 epsilon x and negative 2 epsilon x prime, have the same distribution. So these are the same thing because I'm taking the expectation on the same distribution. So I get twice this, so 1/2 goes away. So you can see I paid like a 2 inside the phi, but I managed to get rid of the expectation. So that's the basic idea of symmetrization, which works for any convex function. Does that make sense? Questions? So this is the basic idea. We're going to do a more sophisticated version of the same thing. Right? For example, this doesn't make that much, for example, improvement if this is like x squared, for example. You get something like 4 times x, like expectation of x squared. But for some more interesting functions, it might be some non-trivial. So now something that we can sort of get rid of this epsilon easily. If there was absolute value again, the epsilon would go away. It gives you a bound, but for some convex functions, it's much nicer. Questions? Okay, if no questions, let's do it for the more general setting. So suppose I have now z was, so these were IID. So IID coordinates drawn from P. And now I build an independent copy of z. So that z prime has n coordinates. And then I have a Rademacher. So this should be Rademacher to the n, basically. So epsilon is epsilon 1 up to epsilon n. These are IID Rademacher, independent of both z and z prime. So z and z prime form an exchangeable pair as before. And then I can state the result like this. So if I apply f to z, so what I mean by f to z is like f of z is just, I'm going to do it like coordinate wise. Okay, f is a function defined on the z space. So by f of z, I mean something like that. So this quantity is just f of z1 minus f of z prime 1 up to f of zn minus f of z prime n. And what I'm doing is that I'm looking at these the process basically, or think of it as an infinite dimensional vector. So I'm looking at the joint distribution of these. Okay. You can think of the marginals if it helps, but the reality is that the result holds for the joint. And this is just like the Hadamard, just a compact notation. What I mean here is like epsilon1 times the first coordinate of this, which is f of z1 minus f of z prime 1 dot 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 up to epsilon n f of zn minus f of z prime n. And then f varies. So that's the entire process. So the idea is that the joint distribution of this process and this process are the same. So marginally, they're the same because you can see. So if I, for example, look at each coordinate, f of z1 and f of z prime 1 have the same distribution. And this is just flipping that around with probability 1/2. Right? This is the basic same thing. So it's like f of z1 is some x, f of z prime 1 is x prime. So it's saying x minus x prime has the same distribution as epsilon1 x minus x prime. Okay. But if you think about it, it's a little bit more tricky, but the joint distributions are also the same. So the coordinates are independent, right? And what I'm doing is basically in each coordinate, I'm either keeping the original one or flipping it. Because of independence and because of the fact that all the marginals are the same, the joint distribution is going to be the same. Does that make sense? So this thing is going to be like a random flip in each coordinate. But so independence of the coordinates plus like invariance of the marginals. This gives us this. Okay, so if you think a little bit about this, that's the case. So as an entire process, these processes have the same distribution. Now I'm going to write this quantity. So this is, so what this is if you recall, I'm integrating f with respect to that measure, which is pz. So this is like f of z1, zi, minus f of zi prime. So if you remember what this is, pz is an empirical measure. So f applied to this is averaging of this, and then this is the average of that. And this is, if you recall what pz epsilon is, this is just 1 over n summation I from 1 to n. Epsilon I f of zi minus f of z prime I. And so this is just a simple projection of these processes into one dimension. So you just basically sum all the coordinates, take the average of all the coordinates, take the average of all the coordinates. So these two processes are the same. This is a multivariate process. This is like a univariate, real valued process. Okay, so because these have the same distribution, when I average the coordinates, they have the same distribution. So now these processes, if they have the same distribution, then the maxima have to have the same distribution. There's some sort of measurability issue, but I'm not going to worry about it. Let's say f is finite, then the maximum is well defined. The question is that is the distribution of the maximum determined by the distribution of this process, which is determined by the finite dimensional marginals. But let's not worry about that. Let's think about, I can take f to be finite and an increasing. You can approach the supremum by a lot, like increasing class of finite subclasses, and each one, this makes sense. Actually, defining these suprema, like measurability of suprema, is something that you need to worry generally. You're not going to worry in this course. There are ways to deal with it. One way is just to work with finite classes that grow. But let's say if this was finite, it's perfect. So we'll have like a vector. I'm taking the maximum of the coordinates, the absolute value of the coordinates. So this is basically max. Or let's say sup. Remember, this is sup f in f, f pz minus pz prime. And this is the same thing, sup f f p z epsilon minus z prime epsilon. Okay, so these suprema are the same. No, not the same, the distribution is the same. Okay, so we have this so far. Is this clear? People are okay with this? Okay. Then we have this result that we can say the expectation of the suprema of pz minus p is bounded by twice the expectation of the suprema of the Rademacher process. So this is the expectation of the suprema of the empirical process. So supremum of the empirical process. This is the supremum of the Rademacher process. So this is saying that within a factor of with a factor of 2, this upper bounds the supremum of the other, which is really good. So it doesn't depend on the class size of class. So the way to prove it is first we look at so remember this function. So if I define a univariate function, not univariate, so take u is like u1 up to whatever the function that takes the supremum of the absolute value of the entries, this is a convex function. Why this is a convex function? So a function that takes one of them to the coordinates, this is convex. This is not hard. So like projection and then absolute value. And then I take the maximum of a bunch of convex functions. Convex functions, it would be convex. Right, so if you think of like 2 convex functions, the maximum would be, this would be the maximum. So in general, the maximum of 2 convex functions and the minimum of, maximum of a bunch of convex functions and the minimum of a bunch of concave functions is, minimum of a bunch of concave functions is concave, maximum of a bunch of convex functions is convex. So this is convex. So this by definition is supremum of this quantity over f. What I'm going to do is I'm basically writing it as, so f pz minus p. Now remember, this is 1 over n, summation I from 1 to n, f of zi minus the expectation of, I can do, let me do it there, something else. Let me do it here. So what we can do is, f p minus, or pz minus p. This is by definition 1 over n summation I from 1 to n. F of zi, I can write it as expectation of f of zi if you want, or whatever there. Then I'm actually going to replace this with z prime. Okay, so the expectation, it doesn't matter with respect to what, it's like dummy variable, as z prime is the same thing. And so I'm going to, I can write it at like expectation under z prime if you want of this. And then I move the expectation outside, things are linear. With respect to z prime, the first term is constant. So I get 1 over n summation I from 1 to n f of zi minus f of z prime I. Okay, and this is the inside, if you think about it, it's just we're integrating f against pz and then minus the integral against pz prime. So if you're comfortable with the notation, that's what it looks like. Okay. Does that make sense? in other words, I can just move this inside the expectation. If you're like imaginative enough, this is like expectation that this is just P. Think of it like this. So I'm moving the expectation inside, passes through this because it's constant, applied to this. This is P. But if you want to be a little more careful, it looks like that. So that's the first step. Then I'm going to pull this out of the supremum. I get an inequality. So why this step is true? That's Jensen's inequality because this is like convex. So this is Jensen's inequality. Jensen's inequality. And then this by definition is just the supremum of this difference. So that's the first thing that we proved, that this quantity, it's a random quantity because the randomness in Z is bounded by this random quantity. The randomness still is in Z in there, okay? But you're averaging over Z prime. So I got rid of the center here. Now I take the expectation over Z of both sides. So if I take the expectation of Z on this side, that's it. And then on the other side, I'm taking the expectation with respect to both of these. So the next step is that I'm gonna, this should be actually equal. I'm gonna replace this with expectation. So the distribution of this guy and the distribution of this guy is the same. That's the thing that we established here. So the distribution of this quantity and the distribution of this quantity is the same. So I'm just gonna replace this difference with the difference in the empirical processes, the supremum of the empirical process, the expectation with respect to every like random, both Z, Z prime, and epsilon. Okay, and then this is like a norm. So triangular inequality holds. I'm gonna break it into two pieces. So this is what I'm doing here is it's like a soup norm. It's norm or semi-norm. This is bounded by the norm of PZ epsilon F plus the norm of PZ prime epsilon F. And then I take the expectation. So the expectation here is just with respect to every randomness that we have. You can take it with respect to Z prime, but there's no Z prime here, so we can drop it. And then here, again, with respect to all the randomness. And then I claim that this is equal to twice this. Why? Yeah, because of the exchange of symmetry. Basically, epsilon and Z, the distribution epsilon and Z is the same as epsilon Z prime. So these two processes, these two quantities have the same distribution. So you get twice that, and that's basically what we have over there. So that's the result. Okay, so it's very similar to what we did in the univariate case, but slightly more complicated because you're dealing with an entire process. But the idea is the same, you can see. The thing is that this Rademacher process has lost the mean here, and then you pay the price of 2. So maybe have a look at this. Any questions? So it's Jensen's inequality and then symmetrization, basically. It's like triangular inequality. This is, let's call this star. This is a star. And the next one is sort of a star again. So if you want to unpack this, this is saying expectation. So this is expectation over all the randomness. This is also expectation over all the randomness. So expectation of supremum F in F, 1 over n, summation I from 1 to n, F of Zi minus the expectation of F of Z1, let's say, or Zi if you want. this quantity is bounded by twice the expectation over all the randoms against supremum f in F. 1 over n summation I from 1 to n, epsilon I f of the I. Okay, so the expectation over all the random is over all the randoms. Okay. That's the compact form of, if you expand what it means, this is the supremum of the empirical process. And so that's it. Like the Rademacher process and the supremum of the empirical process. We managed to prove this nice result. This quantity here is called the Rademacher average or Rademacher complexity. Rademacher complexity or Rademacher average of the function class F. So it has two sources of randomness, the zi's that are coming from the training data and then epsilon i's. So this allows me to condition on zi's and then do some sort of calculations using the VC dimension on that fixed z. As f varies, I'm looking at the restriction of f to that particular vector that has finitely many elements, and then good things happen. Okay, so so that's basically a rewrite of that. So this quantity is called the Rademacher complexity or Rademacher average. So this was the first step. The second step is to show that, so we showed is that basically PNF, sorry, PN minus P, N should be Z. This is an older notation. PZF, we have shown that the expectation is bounded by R and F, twice R and F. That's what we've shown so far. That's sort of the lemma that we had. And then the next step is to show that the probability that PZ, this is a univariate random variable, minus the expectation. It's like you need a concentration inequality. PZ minus P F bigger than, let's say delta is less than or equal to e to the negative something like n. In this case, if the loss class is V bounded, something like that. So we've controlled this. If I can get a supremum, sorry, a concentration that this is very close to the expectation, at least I just need one-sided deviation, then I would get a result like this. So because I can further bound this by that. So if I have a concentration, so concentration inequality, then I can get a result like this. And then from this, I can prove it here. So I'm going to come back to this and do the concentration here, but I just want to do, this is for the next time. I just want to just complete the idea that, so we have that this is close to that, but then this Rademacher complexity is scaled like root e, the VC dimension divided by n. That's the key quantity that this is a measure of how big the class is. I just want to calculate this for the finite VC classes. So once we have this, we have a control over the expectation basically by the Rademacher, and then we show that the quantity is also close to its expectation. Then we have a high probability bound. Even if you don't have the high probability bound, you can have a control on the expectation of the excess risk, because the excess risk is bounded by this quantity. So the expectation of the excess risk over the training is bounded by the expectation of this. So if I have this result without the concentration, I can get like 1/2 expectation of the excess risk of h hat n is already bounded by 2 R and F. right? So if I look at the expectation of the excess, I call it loss. So this is not actually a risk. The expectation of the excess loss is the risk in the decision theoretic sense. So sometimes you write something that this is good enough. Okay, so you're averaging over all the training without the concentration even. This gives you a nice result. It shows that the average excess risk over the training set is like going to zero. If R and F, so if this is going to zero, it's like O of 1. This is a deterministic quantity. Then you have a good result. Okay, so your class is learnable. So before getting to this, let's try to see what is the consequence of another page here. The consequence of theorem 5. So the consequence theorem 5 for finite VC classes. So suppose F has VC dimension V or nu. What I have is that the P n minus, or PZ minus P F is controlled by, the expectation is controlled by the Rademacher average of F, which is 1 over n, expectation over, let's say, Z and epsilon. Soup, yeah, absolute value should be inside the soup, as we had summation I from 1 to n F of Ci. Okay, so let's see how we can control this. So I'm going to control it by, so R and F. So instead of R and F, I'm going to first condition on Z, because they're independent. Once a condition, I just basically can fix Z, take the expectation with respect to epsilon. So condition on Z. So I have, again, soup F in F. Right. Let's just copy paste. Copy paste the same thing here. Okay. So now, how do I control something like this? Let me give you a hint. I'm going to write this as summation I from 1 to n. So I divided by root n, and then f of zi divided by root n. So because I'm conditioning on z's, so let's say I define sort of, this is a fixed quantity. Let's call this AI. Okay, so this would be equal expectation epsilon supremum over f. Okay, that's not, yeah. So, okay, so we have A, which is A1 up to AN. And so as f varies, so f varies in F, so A varies in some set A, and cardinality of A is bounded by E nu over n to the nu. So the thing is, this is like 1 over root n f z1 up to f zn. You can see this is the restriction of f to these endpoints. And because the class is, so the cardinality of this would be basically the cardinality of A would be the cardinality of f restricted to z1 to n. And by the VC argument, this is properly bounded by this. Okay, so the way, like, if you want to properly define it, A is the set of all vectors that look like this. F of x, z1 up to f of zn, f in f. Okay, it's just, this is like 1 over root n, f of z1 to n. It's just rescaled version of these restrictions. Okay, so as f varies in the class, the total number of different vectors that I pick are is just the size of the restricted class, and then this is bounded by this by the Sauer-Schaller. Okay, this part is clear, sort of. So this when I do this, basically what I'm doing is supremum A in A, 1 over n, summation I from 1 to n, epsilon I, sorry, 1 over root n, AI, I put 1 over root n there. We could have just done it without the root n, but it makes sense to define it like this. So that's my current status. So Cauchy-Schwarz. Okay, yeah, so that's a good approach. So can we do Cauchy-Schwarz here? How do we do Cauchy-Schwarz? So basically 1 over root n, summation I from 1 to n. So if I do, what happens? Can you help me? How do I do Cauchy-Schwarz? Anyone? So that would be like, summation. Okay, so what is this? So that's also another 1/2. Cauchy-Schwarz. What is summation epsilon I squared? Divided by n would be 1. So that would be 1. So this would be basically the norm of A. So this bound would give me that, then there's no epsilon, so this whole thing is going to be bounded by the norm of A. And the norm of A is sort of, it's called the empirical norm of the F. So it's like 1 over n summation I from 1 to n f of zi. Squared, this is generally going to converge to the L2 norm. So very like approximately the L2 norm of F, dp, basically. So it's not going to be 0. So this is bounding the Rademacher by something. And then, so what I get is, so this is like in the, so this is going to be bounded by the supremum. Expectation epsilon, supremum over A. And so it would be like bounded by the diameter of the set, or something like this, which is generally not going to 0. So it's interesting bound, but it's not helpful. Like if you do Cauchy-Schwarz here, it's the first thing that you would think about, and it's going to destroy the property. So what better thing can we do? Maybe you guys can think about this for the next time. So the thing is, these are IID, and this is a sum of a bunch of IID random variables. It's close, but let's say even for a single, let's say I fixed A. So the Cauchy-Schwarz give me that this is bounded by the norm of A. But this is much smaller because this is the sum of a bunch of zero mean random variables, right? And so you'd expect the expectation to be very close to zero. But actually expectation is zero. And this is how I, the random variables has to be close to zero. Okay, so you can do a better thing. So you can bound this probabilistically. So this is like a worst case bound. So if you think about the Cauchy-Schwarz, this is like worst case. It's a good bound in general, but in this case, it's really bad because you lose the fact that this is a sum of a bunch of zero mean random variables. You can use concentration inequalities here. Okay, this concentration near the mean, which is zero, so this is actually close to zero. So for the next time, maybe you can think about this. I'll post this. Think about how to bound this. If you have taken 200C, you should know how to do it. So this is, for example, epsilon i's are sub-Gaussians, and this is the sum of a bunch of sub-Gaussian random variables. This is a supremum of a sub-Gaussian process, basically. It's a very good exercise to try to think about a better bound for this. And okay, so I'm gonna stop here. Next time we come back. Okay. Thank you, guys. Is there a VC dimension for continuous loss? There are equivalent versions. Yeah. So either I'll talk about it, or you guys can. If I didn't talk about it, you guys can like pick it up as a project. There's like fat shattering coefficients and things like that. There are other things that you can do for continuous loss, which is sometimes more powerful, like controlling the entropy. But it's a very good question. So either you look it up. I don't know if I will have the time to talk about it, but remind me if you have time. I can come back to it and talk about it. Yeah, thank you very much. See you next time.